Okay, so here we're going to use our mean variance utility function, but we're going to have two variables. So let's see. What I have is we're going to invest in three assets: the risk-free asset, risky asset 1, and risky asset 2. So we can write out our utility function as a function of the return on the risk-free asset plus the excess return on the first asset and the excess return on the second asset. So the one thing we have is maybe WF equals 1 minus W1 minus W2. All right, so whatever W1 and W2 are, we can know how much we're going to invest if the sum of these is less than 1 in the risk-free asset. If the sum of these are less or greater than 1, we're going to borrow at the risk-free rate. So here's our expected return on our portfolio. This is the variance of our exposure to the risky asset. So it's our mean variance utility function. So we're trying to maximize our utility by finding the values of W1, optimal weight in asset 1 and asset 2. All right, so get rid of that. So let's see where we have our W1s. So what we can do, take the derivative with respect to W1. So we get our risk premium of asset 1 minus A times, the 2 crosses out with a half. W1 times the variance of asset 1. This 2 crosses out with a half, plus W2, the covariance between 1 and 2. And the second derivative, the derivative with respect to the second weight, it's going to be very similar. So it's exposure, or the risk premium of asset 2 minus A times W1 times the covariance of 1 and 2 plus the W2, half crosses out with 2, times the variance of 2. All right, so incidentally, we can write this in gradient form as the same thing. It's just expected return of asset 1 minus A times weight 1 variance of asset 1 plus weight 2 times the covariance of 1 and 2. Excess return of asset 2 minus A times weight 1 times the covariance of 1 and 2 plus the weight 2 times the variance of asset 2. And if we're going to optimize this, we set our first order condition equal to 0. So over here, we have two equations, both set them equal to 0. Or we can set our Hessian equal to a vector of 0, 2 by 1 vector of 0. So incidentally, this Hessian can be written as a vector of expected returns, or excess returns, plus, and I guess it would be a minus, scalar A times, let's factor out the W's. Oh, okay, so this is what it relates to. So we can bring the A over to the other side. So let's bring that over to the other side and solve for the W1 and W2s. So let's see what we have. Let's refer to this matrix as an R matrix, a 2 by 1 matrix of excess returns, equals, let's call this an A times a covariance matrix of the assets. So variances on the diagonal, covariances on the off diagonal, times a 2x1 vector of weights. So we can solve for this using matrix algebra. So we can solve for this. Okay, let me the right pen. All right, so we have our optimal weights is going to equal, I guess, divide both through by the scalar. So it'll be 1 over A, and take the inverse of the covariance matrix times R. All right, so this is the multivariate equivalent of what we had before. Is the weight is inversely proportional to the risk aversion coefficient. And this is kind of like the dividing through by the variance. And as the risk premium gets higher, we want to hold more weight in that. All right, so now let's look at our second order condition. So we take the derivative of u with respect to W1, take the second derivative with respect to W1. So that's negative A variance, and take it with respect to W2. So it's going to be negative A covariance matrix, and take this with respect to W2. So that's negative A times the variance, and respect to oh, sorry, it's dumb. This expression in here should be with respect to W1. So it's negative A covariance matrix with respect to W2, negative A variance. So we can factor out the scalar. And so this ends up being negative A times, the covariance matrix. All right, so if we take the principal minor here, take the derivative, that's the determinant. So it's going to be negative times, the variance is always positive, so that's negative. And here you take this, so it'll be A squared times the variance of asset 1, variance of asset 2, minus, A squared times the covariance of asset 1 and asset 2 squared. So as long as, I guess the absolute value of the correlation is not equal to 1, this is going to equal a positive number. All right, so what we have here is a negative positive pattern. And so if we go up to our little rule here, negative positive means the Hessian is negative definite. So yay, we get a positive number. All right, so I don't know what I did here, but anyway, I guess I better quit while I'm kind of screwing up and getting messy. So